Okay, so it's very easy to understand velocity. What is that? What is velocity? It's how fast you're moving across space, right? Or how long you're taking to go from one place to the other. What about acceleration? No, it's not that. What is acceleration, Chris? What is acceleration? Yeah, we're reviewing concepts right now. What is acceleration? What? Speed over time. Good. Which means what? How fast you're doing what? No, that's velocity. Hold on. Yes. Don't give this answer for hands. I know, but it's like his expression. Hopefully you get called on it. Alright? So that's how it works. Alright? So, but yeah, it's how fast velocity is changing. Now, velocity and acceleration, that's not actually right, because that would be the scalar version of it. Velocity is not just how fast you're going through space, but also in what direction you're going. And acceleration is also what direction you're going. Force is applied energy that actually makes you accelerate. Right? Mass is the quantity of inertia. These are all things we learned about so far. Right? Displacement, all right? Distance. These are physical quantities that we learned about so far. Last topic, we learned about some more physical quantities. We learned about potential energy, right? Which is the stored potential to move, either on a spring or gravitational. We learned about work, which is the amount of energy that was applied over a distance to make something speed up or gain potential, right? We learned about the work energy theorem. If you do work, you've got to gain mechanical energy some way, or lose it, right? If no work is done, then you can't change mechanical energy, and that means you can only exchange potential and kinetic, right? These are things we learned about. Today we're adding a new key term, momentum. This is the one that most people have problem understanding. Okay, so what is momentum? Let's try it again. Orlando, have a try it. Try to define momentum for us. So what's velocity again? And what in momentum, he said it. What was the formula? He said it. What was it? Mass times velocity, right? Okay, so if that's momentum, okay, what is it? Is it velocity? Not really. What would be the unit of it? Okay. Is that a familiar unit that we've seen before? Not really. Look, work wasn't joules, right? Now remember, that was force times distance, and force is in newtons, and newtons is kilograms, meters per second squared, right? But then you also have to put distance there, which is in meters, so it's meters squared, second squared. That is similar, but it has this quantity here, kind of square rooted. You see that there? Right? So, but not really. And then we have a name. We don't have a name for this one. It's the one that doesn't have a name. But notice, though, that if you get the newtons as kilograms meters per second squared, right, and you divide by meters, you can get, actually, don't divide by meters. Well, never mind. But anyways, this doesn't have a name, all right? It's the only unit that we have in physics without a name, all right? But that's what it means. Now, it's like how fast your mass is going. So people confuse kinetic energy with this a lot, because kinetic energy is your energy of motion, or how much energy of motion you have. Momentum is not that. Momentum is the quantity of motion. Remember how I said mass was the quantity of inertia? So momentum is the opposite of inertia. So it's the quantity of motion, how much you are moving. Are you with me? But in a way, you can be moving and have momentum and be in an inertial state if you're moving at constant velocity. Does that make sense? Right? So if you're moving at constant velocity, you still have momentum. Right? So the Earth has a lot of momentum. It's been spinning with that momentum since its formation. And since nothing is really slowing it down much, it keeps rotating. That's angular momentum, but its momentum is the same. We'll get to that later in the year. Actually, those topics we kind of brush over, but we still better talk about it. All right? But momentum is like your quantity of motion, right? So it's the object's, how much is it moving? Now, why does the mass matter? The first person to actually think about this was not Newton, it was Galileo. All right? We're going to do this. We can do this lab, by the way. I always tell you to do labs. You can always choose sometimes not to do it. People did the energy lab, but did not turn it in yet. Make sure you turn it in to get the points for it. All right? You can get 100 points to finish it. Right? Here's another one you can do. It's called Galileo's craters. This is how Galileo figured out momentum. Right? He noticed that if you went up to a certain height and dropped objects with different mass, they would fall at the same rate, as long as they were following the same path. Now, we talked about this. If something goes down the incline plane like this and the incline plane like that, they get down there with the same velocity, but with different accelerations, which means it takes longer for the one traveling a greater path to get there. But if you're talking about an object falling from the same height, following the same path, it would follow the same rate and hit the bottom of the same velocity. Galileo figured this out, the whole gravity thing. But he also noticed something interesting. Although the objects will follow the same rate, hit the bottom of the same velocity, the hit was different. You notice that? Because if you put a sandbox, and then let the droplets fall, the craters are different. Are you with me? So they leave different craters on the sand. So Galileo expressed that as like, okay, so they're falling at the same rate, but the motion is not the same. And then for people that don't understand that, he talked about these craters, right? So what the impact that was made is directly related to the energy of motion the object had, or the quantity of motion, sorry, which is momentum. Does that make sense? So you can actually measure the area of the impact crater and directly relate that to the momentum of the object. And that's what the lab is about. It's called Galileo's craters, right? So you just literally, prepare a sandbox and you drop objects different masses on it, different weights, literally different weights, and you quantify that and you try to estimate the velocity. Now, as a kinematics, you can figure out how fast the object hits the bottom, dropping from a certain height, right? So if you know the height, you should be able to know how fast it's hitting. So you do that for the first object. And then you have the second object with a different mass. You should be able to predict, falling from the same height, it would hit the same velocity. But since it has a different mass, you should be able to predict the crater size the second time around, right? Because it's directly related to the momentum. You know what I'm trying to say? And so that's kind of what the lab's about. It's an interesting lab, but that's what Galileo did. He showed that mass matter. Mass does not matter for the way in which it falls because it cancels out. We showed you this before, right? How it cancels out, right? In a way, right? So if you look at an object falling, weight, right, equals mg, right? So weight is the force that's acting, which equals to ma, right? So then a is just g, no matter what the mass is, right? So that's kind of like the dynamics way of thinking about it. We also explained that, yes, one has more mass, which means there's more weight, but there's also more inertia, which means it's harder to move the mass. I talked about that, right? So that explains why things fall the same way. Now, this concept of momentum then is the quantity of motion. Does that make sense? Now, if something with more momentum hits you, does that hurt more or hurt less? It hurts more. Newton realized that. He said, okay, the craters are an indication of the force of impact. So he said there's a direct relationship between momentum and this force of impact, or how strong the impact is. Now, you know Newton's laws? When he actually derived his laws, it wasn't F equals ma at all. It was all in terms of momentum. Right? We're going to show you this in a second. Right? So then, if you think about this thing, there's another thing that's called impulse. Right? So impulse, according to Newton, is how much force is applied over a period of time. Now remember, how is it different from work? Work was what? Force times distance. This one is force times time. Right? So he's saying it's force over a period of time. Now, we can also write the force using dynamics as a ma. Right? So in a way, right, this is like, I'm going to erase this later, but I just wanted to show you something cool. In a way, this is ma times time. Now what's a? That's velocity, right? Over time. Isn't that what he said? So that's just mass times velocity divided by time times time, which is just what? Mass, but isn't that what that is? Right? So you have to realize that using this kinematics, you write a couple come up with that there's a direct relationship between impulse and momentum. And that makes sense conceptually. The more energy, the more quantity of motion you have, the more force you can apply during a certain amount of time, right? So there's a direct relationship to how fast you're moving and how mass you carry to the force of impact. And that was a huge achievement in thinking of physics. So why aren't you scared of being hit by a bug flying at 80 miles an hour? Because its mass is so small. Because its mass is so small, it carries little momentum, meaning it can impart a very small impulse, which means that the force of impact is going to be very small, even if the time is very small. All right? By the way, I'm going to show you that. It's force, therefore. What is really force? By the way, I simplified the formula here when I was looking at it a little bit. It's actually not what acceleration is. Acceleration is not velocity divided by time. It's really velocity final minus velocity initial, right? It's change in velocity divided by time. Does that make sense? Times time. So then the times gets out, but then you still have this. So that's not really momentum, really. That's momentum final minus momentum initial. Are you with me? So if you look at it like that, that equals really the change in momentum, right? So whatever momentum you lose can become force. Does that make sense? All right? That's another way of thinking about it. So really, that gives us the impulse momentum equation, which is this one right here. Impulse equals the change in momentum, right? So you can also rewrite this as change in momentum, and therefore mass, velocity final, minus velocity initial, right? And that's really the formula you need for this chapter. So then we can get rid of the rest, all right? So now remember the momentum and impulse are in this weird unit, kilograms, meters per second, right? Which you can't really, there's no name for it, right? All right, so then anyways, the idea here, we're going to solve for force. So let's solve for force, because you know force equals ma, right? Well, it's not according to Newton. Force is not equals ma. Local force is according to Newton. We get these two things, and he says what force actually is a change in momentum divided by time, or the rate at which your momentum changes. Now remember how let's go back to the first law, and this is something that showed up in the GeoQ, but we have to talk about. So what was Newton's first law again? Let's help you out. Anna, what was the first law of Newton? Okay. First law. Come on. You got this. First law of motion. Yeah. What does that say? Basically. Don't look it up. You know this. What does it basically say? That in order for you to change momentum, what happens? Not relation to this, but in general. Like, what does it say? What is inertia? An object. Everybody knows this one since middle school. An object in motion. What is it? All right. Remember how I said I didn't like that? That I liked a better way of saying it? That the motion pattern cannot change unless a force applied to it, right? The object's quantity of motion or momentum cannot change unless a force applied to it. That is how the first law can be stated, right? The second law can also be stated this way. The rate at which momentum changes is dependent on the force that's applied to it. Now remember that this is basically mass final minus mass. Do you know what that is? Right? V final minus V initial. That's what that is, the top. And the bottom is just change in time. You can look at this part here, and that's acceleration, isn't it? So then you back to F equals ma. But that is how he expressed his law, not F equals ma. Right? And there's a deeper understanding when you look at it this way. Basically what you understand that is that what does force do when it's applied over a period of time? It changes how the quantity of motion. But there's other deeper understandings from this looking at this formulas like here. Let's think about something else that can happen. Right? Now, ever heard about thrust? Right? It makes rockets launch and stuff. It also, can be used in a that's what she said connotation. But if you think about thrust, what happens, let's talk about a little bit of third law now. Third law. What happens in the third law if I throw something, what does that mean? Something got through me, right? Which means whatever momentum cannot change. The third law, right? The momentum of a system, cannot change. Notice I just rephrased all three laws in terms of this. I don't know if it's on the GLQ or not. I think it is. Yeah. But it's number one, isn't it? So let's talk about that slowly. So what was the first law in terms of this? An object's momentum cannot change unless a net force acts on it. Is that cool? Now the second one was that the rate at which momentum changes is force. Right? Force is the rate at which momentum changes. Does that make sense? Third law, the momentum of a system cannot change. So you see how elegant the laws become. All of them become in terms of momentum. And that's how he phrased them. Right? He did not phrase them in terms of that. Because look, if I do it in terms of dynamics, it's like this. An object's acceleration cannot change unless a force is acted on it. Acceleration is force divided by mass. And the third law is whatever force you impart on something gets imparted on you. It's like you're changing the motif between acceleration and force a little bit. But when you put it in terms of momentum, everything is in terms of momentum. Momentum cannot change unless a force is put on it. The rate at which momentum changes depends on its force. And then the last one is that you cannot change the momentum of a system. Let's see what that means though. That means is that if I give something momentum, it means that what? I lost just as much. Does that make sense? It also means that if something suddenly gained momentum in a system, something else must have what? Does that make sense? This is going to be very important in collisions as we get to the end of the class today. Right? I'm going to start on it. So it's very important to think of it that way. Alright, so where were we? That was number one? Alright, so then I was telling you about some realization that you can do here with impulse. That's kind of cool. Probably getting ahead of myself also, but remember, take notes when I'm talking, because this is all very important. But anyways, impulse. Impulse is thought of as a type of force. Right? Now as you really look at what force is, this way, right? Force equals change in momentum, which I'm going to phrase it like that. Change in momentum. Change. Well, what is momentum really? Mass times this, right? Now, and then divided by time, of course. Okay, or change in time. So, the quicker this happens, the more force it is. Which means what about collisions? When does it happen very fast? More impulse or less impulse? More impulse. Does that make sense? If the collision happens very fast, you get more impulse. Look at that. That's why cars crumble when they collide. That's why airbags exist. Right? Because when you collide, the crumbling of the car makes the collision what? Right? Also, the airbag, when you're hitting a wall, it's an immediate collision. But when you're hitting cushion, it's slow. When you hit water, the collision happens instantly or slowly over a longer period of time. Remember we talked about this in another GLQ? Why does it hurt less to hit the water? And it's about the time. Because it reduces the acceleration since you have more time and more distance to slow down. Does that make sense? It makes sense this way as well. But there's something else here that's interesting. We think of velocity, velocity as something that can change, but not mass. Right? But you can realize that's not true. You can change the mass. So for example, let's say I am going I'm in a rocket, launching into outer space. This is literally rocket science. Should have wear my rocket science shirt today. All right? If you're going into outer space, how does it work? People think about it works with the third law. How does a rocket launch? What's actually pushing the rocket up? Think about it. What's pushing the rocket up? Hold on. Let's see Justin. What do you think pushes the rocket up? It's thrust, but how does that get generated? Just think about the rocket as a free body diagram. Isn't it accelerating upwards? So that means a force must be pushing it upwards. What is that force pushing it up? Where's it coming from? Come on, think about a rocket. What's pushing the rocket upwards? The exhaust is coming from back there? Okay, good. All right. But what is the rocket doing to the exhaust? Is it throwing it in which direction? All right, so what's really pushing the rocket up? The exhaust is pushing the rocket up. Does that make sense? Let's go back to the rope climbing. When you pull a rope down, what happens? The rope pulls you up. Does that make sense? So that's how it works. So the same thing's happening to the rocket. But that's only half the story of how thrust works. Yes, you are thrusting something out, you're throwing something out which pushes you out back. But at the same time, what is happening to the amount of fuel inside the rocket? What's happening to it? What does that mean about the mass of the rocket? It's decreasing. So what's happening to this? It's getting smaller. Right? So that means as time goes by, there's actually a change in mass also. Right? But you can't change momentum. Right? Of a system. So if mass is going down, right? You can't change the mass of the momentum of the system. So that means if mass is going down, velocity has to go up. Does that make sense? So you also gain, there's a second explanation for why rockets will go up. Right? It's not just the third law. It's that also that as you lose mass, that would cause a change in momentum. That's not possible. You cannot change momentum of the system. Therefore, what happens still happen? Does that make sense? It's a simple way of thinking about thrust. There's a more complicated way of thinking about it, but it's a simple way of thinking about it. Does that make sense? Right. I will be right back. Keep working the GLQs. I just gotta get it right back. Continuing, Jennifer, what is question 2? Don't answer it, just ask the question first. You shoot a bullet, okay? Alright, so let's think about that. Kinetic energy or momentum? Okay, so think about kinetic energy. So you're shooting a bullet. Now, true or false? Both the bullet and the gun receive the same force. True. True or false? After the explosion that happens inside, momentum cannot change. True. Right? So whatever momentum the bullet gained, what it means about the gun. Alright, so that means the momentum of the bullet. By the way, momentum is a vector. That's another thing we talk about. This is actually a vector. It has direction. Alright? So that means the momentum that the bullet gained, going that way, has to be equal but opposite to the momentum of the gun. Right? So this momentum will be negative compared to that momentum. Why? Because if that's true, right, if it wasn't true, this wouldn't be true. Right? You need this to be true. And why do we know that's true? Because you cannot change momentum of the system, right? So now, if that's true, then now, if that statement is true, we can rephrase it as the mass of the bullet times the velocity of the bullet equals the mass of the gun times the velocity of the gun. Does that make sense? This is the first classic example of momentum problems you're going to see, right? You're going to see 3 types of momentum problems. Things which work together, splitting and separating it, which I call them explosive situations. Are you with me? Here's another explosive situation, right? So if I'm sitting on a skateboard and I throw something out of it, it's 2 things separated. Are you with me? You also have situations like this, when 2 things come at each other, right? And then combine. So it's the opposite, right? When you have the merging thing going on, all right? You also have the situation where things hit each other and then bounce back from each other, right? So these are the three types of collisions that we're going to talk about in the next lecture, but hopefully we're going to get to that today. So we're already actually talking about the first aspect of that, right? So in this situation, the momentum of them must be the same. Now, just thinking about it, right? You understand why the velocity of the gun is smaller? No? Why? Because the velocity of the bullet, so they have to have the same momentum, correct? So this number on the left and this number on the right is the same. But this number is a lot smaller than that number, right? Which means this number has to be a lot bigger than that number. So they are the same. Right? That makes sense. Yes. Now, so that answers an issue of momentum. But what does that have to do with kinetic energy? There's another secret of these problems. Because the same things are in the kinetic energy equation. You have m and v squared, 1/2 mv squared. Right? So then, which one has more kinetic energy? The bullet or the gun, they ask. Well, so then let's talk about the kinetic energy of the bullet. Right? What would that be? That would be 1/2 the mass of the bullet times the velocity of the bullet squared. Well, what is the velocity of the bullet? Right? Well, we can phrase it in terms of what we find out from here. You see that? That's solving for velocity of the bullet. Right? So I'm going to do that. And then we have 1/2 the mass of the bullet. Make sure you write this down, guys. It's important. Okay? Times, now that's thing, the whole thing there squared. So it becomes the mass of the gun squared, the velocity of the gun squared, divided by the mass of the bullet squared. Right? Now, this one cancels out with one of these, and this is the final term that we have for it. Okay? That's the kinetic energy of the bullet. Now, if you think about the kinetic energy of the gun, it will be the same thing in reverse, right? For the kinetic energy of the gun. Because remember, velocity of the gun, if I solve this thing here for velocity of the gun, I get mass of the bullet times the velocity of the bullet divided by mass of the gun. And this is going to be 1/2 the mass of the gun times velocity squared, or mass of the bullet squared plus velocity of the bullet squared divided by mass of the gun squared. One of these cancels out one of those. So now let's think about numbers and compare them here. All right? Think about it. This mass of the bullet is a big number or a small number? Small number. The mass of the gun, big number or small number? Big number, okay? And you're squaring that big number. So you're making a even bigger number, right? And then this number, mass of the gun, velocity of the gun, big but not as big as this number is. Does that make sense? So I'm just comparing terms here, all right? Mass of the gun is on the bottom here. The mass of the bullet is on the bottom here. Which one is bigger? The bottom here is bigger. Which, if it was just that, then would make this number smaller than that number. Does that make sense? Because that is dividing more out of it, right? So that means, or dividing into more parts. So if it was just based on the denominator, this one would be smaller, right? But then there's also the numerator. The velocity of the bullet is on this term. How fast is that going? It's very, very fast. And then mass of the bullet is there, not as much, right? So, which one, when you look at it that way, looks like it's more? Which term? This top or that top? Looks like a bigger number. It seems like a trade-off, right? Because here you have the mass of the gun that's a lot more, and here you have the last bullet that's a lot less. Here is the mass of the gun, which is a lot more. Velocity of the gun, which is a lot less. Here's the velocity of the bullet, which is a lot more. So which one wins? Right? It will be the same. Well, you need numbers to know for sure. But instinctively, let's think about this. Which terms matter more for kinetic energy? Mass or velocity? Velocity, right? Now, if the velocity of the bullet is even 100 times more than the velocity of the gun, after the recoil happens, right? You're going to square that, and it becomes 10,000 times more. That means the mass of the gun would have to be 10,000 times the mass of the bullet to make it equal. Do you think that's true? No. And so, instinctively, we expect the bullet to have more kinetic energy, right? But which one? Are you with me there? So now, where do we see the momentum situation? It's hard to ask the kinetic energy question, but what about the momentum question? Which one has more momentum? All right. right? But yet one can have more kinetic energy than the other. Does that make sense? Which means that's, all right, so let's continue from there. That's the first thing that I want to introduce. It's possible for the objects involved to have different kinetic energies. Now, also another thing that happened there. Did you make energy? Where did that kinetic energy come from then? Yes. From where? No. All the momentum, you never changed momentum. How much momentum did you have at the beginning? No. How much? It was zero. How much momentum do you have at the end? Zero. Because whatever positive momentum one has, the other one has negative. Does that make sense? So momentum did not change. So you have no change in momentum, but you have all this sudden increase in kinetic energy. Where is the energy coming from? What potential? What propels this bullet? The gunpowder. So it's actually the potential of the chemical energy stored in those bonds that exist in that chemistry. You know what I'm trying to say? There was an explosion that released energy. A lot of it went to heat and sound and noise, right? And seismic waves. But a lot of it went to kinetic energy of both objects, right? Yes? All right, so see what's the actual problem you're talking about? Find out which problem it is so we can go over it in a second. Let's finish the GLQ first. All right. It sounds like something I definitely should look at too. You should always do that, by the way. If you guys stuck in a problem in practice, you don't understand it. All right, what's number 3?
Yeah, 3 is talking about...
It's fine. So we're teaching everything. All right? So I'm going to leave these formulas on the board because we're going to need it, but I'm also going to erase things so we can do the problem. All right, number 3. Somebody read the problem out loud.
2 objects approach each other with velocity such that the total momentum of the masses is 0 kilograms meters per second and undergo an elastic collision. Is the sum of the kinetic energies of the...
Let's skip it. Because it's collision. All right, let's go to the next one. Let me see here. 4 is also collision. 5 is collision. All right, let's do 6 for now. Okay, so state if it's true or false and explain your answer. All right, a particle that has 0 momentum must also have 0 kinetic energy. So 1, let's look at our formulas here. I'm going to put kinetic energy on the board so we remember it. So a particle has 0 momentum. Does that also mean it has 0 kinetic energy? What does it mean if it has 0 momentum? What is the particle doing? So what is kinetic energy? Is that true or false then? What do you think? What? You have the statement says a particle with 0 momentum must also have 0 kinetic energy. True or false? True, right? Because of the formulas, right? The only way you have, if it's a particle, what is the only way to have no momentum? Unless it's a massless particle, you'd have to have a particle that's what? Let's talk about massless particles for a second, because this is fun, right? An electron doesn't have any mass. Can it have momentum? Look at it. Mass of the electron is 0. Can it have momentum? Because it has no mass, right? That's actually not true. Not an electron, sorry, not an electron, a photon, a particle of light. A particle of light has no mass. If you have no mass, can you have momentum?
Yes, because
The rain is expecting you, like, how could you have, you're plugging in 0 here, there's no way, right? Now here's something that's cool that I like to introduce. E equals mc squared. You know this one?
Yeah.
All right. So for this value to truly be 0, it doesn't mean necessarily that you have to have mass, because mass can be E over c squared. So if you have energy, you have mass. So as long as light carries energy, it actually has mass. Does that make sense? What? The only way for something to have no momentum is to have no mass and no energy. Does that make sense? But since photons carry energy in the form of, light radiation, they actually have momentum. Proof. You can actually use photons to make something move faster. Have you heard about solar sails? No? It's a theoretical concept of literally you put a sail that catches photons. As the photons hit it, light, literally, it pushes the spacecraft forward. Alright? Now, experiments have been done on this, and it's true. Photons can actually have an impulse. Does that make sense? If they have impulse, it just means they can lose momentum. Right? So that means photons do have momentum, and it's just interesting too. I just want to plug that in there. But anyways, that's number A was correct. B, yes, I have a question. Yes. What is an example of that? All right. That's a good question. It's a good question. I don't know.
He was exactly. Yes.
I don't know. Yes. All right. The next one. Follow along. A system that has zero momentum. Now we're talking about a system. How is it talking about a system different than talking about a particle? Now, a system, first of all, can have potential energy, can have kinetic energy, can have momentum. Now, this system has no momentum. What does that mean? When you add the momentum of all particles, what's the total momentum? Does that make sense? All right. So a system has no momentum. It must also have no kinetic energy. All right. So let's think about that one. Let's see who this is. Susan, what do you think? The system has no momentum, and it has no kinetic energy as well. Okay. So, the best way to answer this question is think if you can think of an exception. If there is an exception, then it makes the statement false. Alright? So, we are in a system right now. Right? Most of us are stopped. But there's also particles inside this room moving back and forth. Are you with me? These are gas molecules. But for every gas molecule going this way, there's one going that way. Such that the momentum of this classroom is zero, most likely. Are you with me what I'm saying? Because all the gas molecules cancel each other. Nothing that happens within the system can change that. Is there kinetic energy in the system still? Think about the molecules. Aren't they moving? So is there kinetic energy here? In fact, temperature, we're going to learn about this later in the year, is directly related to kinetic energy. So since we're not an absolute zero over here, is there kinetic energy in this room? But there's no momentum. Right? So we know there's an exception. So it's easy to think about it though. If I have a particle of mass 10 and another particle of mass 10, this one is moving velocity 2, this moving velocity 2. What is the momentum of this particle? Come on. Mass 10, moving at 2. What's the momentum? No, it's not 20. Moving to the left. Negative 20. Alright? What is the momentum of that particle? 20 also doesn't mean anything. You got to put the units. It's kilograms meters per second. Right? Now, just the same time. So, that one's negative 20. That's positive. What is the momentum of the system? 0. Now, what is the kinetic energy of that particle? Well, it's 1/2 mv squared, right? So, v is 2, so it becomes 4. Half is 2 again, times 10, 20. And that one will also be 20. What is the kinetic energy of the system? 40. Are you with me? So you have 40 joules of energy, kinetic energy, but 0 momentum. The key is kinetic energy is a scalar. It just adds up, right? More and more. But momentum is a vector, so they can cancel each other out and have 0. Does that make sense? All of that stuff that I just talked about, you're smart, you wrote this down because it's a good review. All right. C. A net forcing acting on an object is equal to the rate of change in its momentum. So let's translate what they said. A net force acting on an object equals to the rate, that's what a rate means, of change in its momentum. Is this true? Didn't I put this problem before earlier today? And it is, look at that. You look at these two and divide both sides by delta t, you get that, right? So that is true. That is in fact, you can just write it. True. That is a statement of Newton's second law. Very good. Label. Right? Okay, make sure you're getting labels if you're participating, people. impulse is delivered to an object. Okay, the impulse delivered to an object is equal to the change in the object's velocity. Let's see that. The impulse delivered to the object is equal to the change in the object's velocity. Let's see if there's any of these equations that make sense with that. Right. If I do that, that doesn't make sense. If I do that, that's impulse equals change in momentum. That doesn't make sense. If I look here, it almost says there a change in object velocity, but it's not a change in velocity. It's change in object velocity times the mass, right? So that statement is false because it's missing what? Times the mass. Does that make sense? Right? No, it's not equal to change in velocity. It's equal to changing what? Pay attention. It says it's no. The impulse delivered to an object equals to the change in the object's velocity. No. The change in the object's what? What is impulse equal? The change in the object's what? Momentum, not velocity. Alright? That's what's wrong about it. Internal forces cannot change the total kinetic energy of a system. Right? So we're in the system, right? Now it's just you, us. Forget the gas bubbles. I mean, we're erasing that from the room. Alright, take a deep breath. Right, so sound will not travel though, so that doesn't work. But anyways, ignoring all the gas molecules, we're just us. Everyone stop, please. How much momentum is there? None. How much kinetic energy? None. Can we change that from within the system itself? Can we change the momentum in this room? You do not change the momentum though. Because as you walk, you're pushing the floor backwards by just as much. So you cannot change the momentum. But can you change the kinetic energy?
Yes.
That's a very good point. So I throw a Lego at you, right? Then I add momentum to the room. No, because as I threw that, I did an impulse, right? An equal impulse was imparted on me. That means no change momentum. Yes?
So, if momentum is only zero.
No. In a system, change momentum is zero. A particle can change momentum, but a system can't. Unless, of course, a force acts from outside the system.
So, like that Lego changed momentum.
Yes, and I change momentum.
But not.
But the Lego knee system did not change momentum, right? Another thing that's important, could you change the momentum of the system from outside of it? Certainly, right? If the system is this Lego box, I can change momentum by doing that from outside of it. Are you with me? But if I'm talking about the Legos inside that box, they can't change the momentum of the system. Are you with me? Now, the universe is a system, right? So in a way, you cannot change the momentum of the universe. Because a force would have to come from the outside of the universe to do that. That's what's happening. The universe is going faster and faster by a mysterious force that nobody knows what's causing it. Right? The dark energy is called, right? So that's breaking that rule, which shows us what about the universe? It's not a what? It's not a self-contained system. There's got to be something outside of it. Are you with me? Or there's a mysterious thing inside of it driving it faster and faster. Or there's something else losing energy as that's gaining it. It's a mystery of physics because it contradicts basic laws of physics. Right? Right?
Physics is alive.
Perhaps. Perhaps. No, actually, not perhaps. I think I talked to you guys about this at the beginning of the year. Science, everything we teach is wrong. Didn't I talk to you guys about that? We know it's wrong. It's just the best we currently have, right? But anyways, what did I say? You want to say something? Right. Anybody on the earth, can you ever change the momentum of the earth? But can we do something to add kinetic energy to the earth? Right. Every time we jump, we're doing that. Right? Because, right? Does that make sense? Alright? Right, but you can still, by the same token what we're talking about here, every time something starts moving that wasn't moving before, kinetic energy increases. But that doesn't mean that energy is coming out of nowhere, because that requires loss of potential. Are you with me? Or work being done. Right? So in the case of me jumping, yes, I'm adding kinetic energy, but at the expense of the potential energy that was in my muscles. Right? So, or the work my muscles did. Alright. Internal forces cannot change the total momentum of a system. True or false? By the way, the last one was true, right? Internal forces Internal forces cannot change the, oh wait. Internal forces cannot change the total kinetic energy. That's false, right? Internal forces can't change. All right? Because you're basically doing work. So that means you can get kinetic energy. Right? Now, internal forces cannot change the total momentum of a system. That is true. Which law is that? That's the third law, right? That's the third law. All right. Continuing. Yes. All right, it's okay. We're going to have to do it after we finish maybe not today, maybe on the next lecture, okay? Because we have to do it. All right. So how much do we have left for it, though? A lot. Yes, I'm saying that's why I have to do it all. Okay. Identical forces act on the same length of time on two different masses. Right? So identical forces act for the same length of time. So the force is the same, and the time is the same. All right. But it's two different masses. Okay? The change in momentum of the smaller mass is bigger, smaller, or the same. So look, remember the secret of these things is find the equation that need help you. So remember how this is a whole statement of truth here. But you can pick which equalities you want to do. I can do this equals this, I can do this equals this, I can do that equals that. Are you with me? And that's the one I need, if you notice what I mean. Because I actually need this statement to answer this question. A force, because why? I have force in the problem, I have time in the problem, I have mass in the problem, I have change in velocity in the problem, right? So I need a formula that has all those things. So this one. Right? So they say an identical force acts for an identical period of time on two different masses. What happens to change in velocity? My next step is to do what? Solve for the unknown, which is like that. Same force, same mass, different masses. Alright? Then they ask you the change in velocity, okay, of the smaller mass. That means the number that's smaller. When I make this smaller, is that bigger or smaller? Right? Think about it. If I make this number smaller, does that make that bigger or does it make that smaller? This becomes smaller, does that make that bigger or smaller? People, come on. Bigger. Does that make sense? It does make sense with the second law. Less mass, less inertia, you're going to accelerate more. Does that make sense? Alright? Alright. So 8. Two different masses have equal, non-zero kinetic energies. Two different masses. How can you have the same kinetic energy but different masses? Look at the formula. Same kinetic energy but different masses. What does that mean about them? They're going at what? Different velocities. Are you with me? They have the same mass, different masses, the same kinetic energy. Okay, we established that. Continue the question. All right? The momentum of the smaller mass is bigger, smaller, or the same. That's not an easy one, so I'll do it for you guys. But pay attention there. All right? How do I solve that problem? They want to know the momentum, right? So I need an equation for momentum. What's the equation for momentum? V equals mv. Right? Now, what they give me is k. Right? Now I know that k is the same for both. Right? But the masses are different. That means the velocities are also different. Right? But k is the same for both. Right? So the momentum of the smaller mass. Now, let's think about the velocity. What are they asking about? The momentum of what mass? Is smaller or the same? The momentum of the smaller mass. Okay? So the momentum of the smaller mass. Now we just talked about this. If the mass is smaller, but they have to have the same kinetic energy, what does that mean about the velocity of that mass? It's got to be greater. So we know that velocity is big here, right? And the mass, though, is smaller. Does that make sense? Then the second mass, or mass 2, also has a mass in a velocity situation, right? Mass 1, mass 2. Let's think about this. We know that one mass 1, is bigger than mass 2, right? But they have the same K. The only way for this to be true is that the smaller mass, M2, has a bigger V. Does that make sense? So V2 is bigger than V1. Right? In order for the statement to be true. If the mass 1 is bigger than mass 2 but has the same K, that means the V of 2 must be bigger than V1. Right? So we know this number is bigger than this number. But then we also know that this number, V2, V1, is smaller than that number. So it's a trade-off? Not exactly. Because look at this. Velocity here is what? Squared. So do I need a lot more velocity to match the kinetic energy? Not really, because the velocity gets what? Squared. Does that make sense? So I don't need to match the increase in mass. I need less increase in velocity. Right? So this change here is not equivalent to this change here. Right? Yes, this number here is bigger. So I'm picking the bigger number. And yes, this number here is bigger. However, this is much bigger than this is bigger than that. By that rationale. Yeah? That is hard physics there. You have to make sure you understand. Alright, so let's go back it up a little more time. Alright? One more time. K is the same. Correct? But M's are different. What is the only way for that to be true? So if the mass 1 is bigger than mass 2, V2 must be, is anybody there with me still? If you're not, raise your hand. Alright? Make sure you tell me. Alright? If you're not, it's okay. If you still be like, I'm lost. If you lost here, it's fine. The test is not a good idea. If K is the same, I have to trade between mass and velocity. Right? When this number is bigger, that has to be smaller for the numbers to be the same. Right? So that's why I'm saying that mass of the first one, if it's bigger than the second one, its velocity is smaller than the first one. That has to be true for that state to be the same. What I'm saying though, just stay with numbers so you make this clear. Let's put mass 1 is 2 and mass 2 is 1. Are you with me there? Now, think about it. Actually, I'm going to make it easier with making numbers in the tripod drive. Like that. That'll make it easier. Alright? So, by how many times is this mass bigger? I'm going to make it 4 times bigger. 8 and 2. By how many times is mass 1 bigger? 4 times. That means the velocity has to be bigger by 4 times of the other one to make the match happen? No. Look at it. So let's calculate the kinetic energy of that. It says velocity is 1. Right? The velocity is 1. That will be 8 times 1 squared. Right? Divided by 2, which will be 4. So that will be 4 joules. Right? How do I make the kinetic energy of this 4 joules? Because it has to be the same. Right? Look at it. So the mass is 2, so divided by 2, that's 1. So I need that to be 4. Correct? And how do I make that 4? 2 squared. Correct? So that has to be 2. Right? So I need the mass to be 8 here. The velocity was 1 and 2. You see? This number was 4 times bigger than that number. But that number was only what? 2 times bigger than, you see clearly now what I'm talking about. Right? You do not need to increase the velocity by the same factor that you increase the mass, because velocity gets squared. Does that make sense? Now, by the same token, looking at the numbers, by the way, sometimes when you have conceptual problems and you can't understand correctly, you just plug in some numbers and it makes more sense. Right? So you see that there? Now, using the same example, we just did it. This would be 8 and that would be 1, which gives us 8. Right? This would be 2, that would be 2, which gives us 4. So that one's bigger. Right? Why is it bigger? Because the trade-off between mass and velocity is not necessarily the same. Does that make sense? Because the velocity gets squared. So to answer our question, the smaller mass, mass 2, would have to have a smaller momentum. Does that make sense? Smaller mass would have smaller momentum. Right? For that to be true. Okay. Alright. Woo! That was hard. 9 is a collision. Let's skip it. Alright. 10. A freight car moves along a frictionless level railroad track at constant speed. Alright? The freight car is on top. A large load of coal is suddenly dumped into the car. What happens to the speed of the freight car? So that is a collision, actually. Alright? But it's not as hard as a collision. I'll explain how hard is a collision. Remember, I told you there's 3 types of problems. They split, they join and combine, or they join and separate. This is the second one, the join and combine. How do you ask? If you don't see that, think about it. You have a train going, right? And there's a whole load of coal. What do? They dump the whole coal, and then what happens to the coal? It stays as part of the train. So it's kind of like the load of coal and the train of what? Combined. The momentum cannot change. Ever. Right, me? Doing a collision, momentum cannot change. So that means the change momentum has to be equal to 0. right? So let's think about what that means. Let's think about the momentum before. The coal was just stopped, but the train was moving. So the momentum before is the mass of the train times the velocity of the train. What about the momentum after? Well, after, the train and the coal are one. Does that make sense? So you have the momentum of the train plus the momentum of the coal going at a speed. The speed after, I'll call it V2. See what I did there? Is that kind of problem you combine the masses because they become one, right? Now let's think about this. Before, how does this velocity here compare to the velocity there? Just think about it. What am I doing to the mass? Increasing. What does that do to the velocity? Why? Because this number has to be equal to that number, correct? So if I'm increasing this, that number has to go. That's the opposite of the rocket thing. When the rocket loses mass, the velocity goes up because momentum cannot change. Does that make sense? So this is gaining mass. I don't know if you ever noticed this, but we can do it. 5 minutes, we can do it. So I really suck at skateboarding. Is anybody good skateboarders in the room? No? But I need a push. So go over there. Drag me over there too.